Good evening, everyone. Hopefully, we're all feeling somewhat ready for the exam on Wednesday. Hopefully, after today's class, we'll feel even more ready for the exam on Wednesday.
Are you going to give us the answers?
I'm going to give you the problem-solving process so you can solve even more than just my exam. It'll be great.
Good try.
So, for those of you who just arrived, we're going to work on this problem first. Try to think about the approach, how you might use mental analysis or some version of that to answer this question. And while you're working on that a little bit, I'm going to write up some times here for office hours that I'm going to volunteer, and then I'll see who's available for which. So if you are stuck, don't know how to start this, then you can call one of us over, Sarah, Akia, Anil, and myself. Let's go ahead and take another minute or two. Sarah and Akia, do you mind helping you here?
So I pretty much only got as far as the potassium sulfate for like a number of moles, but I don't know what to go.
So then, in every mole of potassium sulfate, how many ions?
2, right? This is a polyatomic, right?
Mm-hmm. So you're saying that when it dissolves, it breaks into what?
So it's just 78.
It breaks into potassium ions and sulfate ions.
How many of each? That's the key to answering this question. Those total ions, yes. How many ions there? Think about it. What first? Okay, so what did you find? What did you get? No, Mary, what did you find?
Bad. I said traffic was bad. They closed? Not now.
So we have 22 responses. Let's go ahead and work through this problem first, and I'll come back to the office hour. How do we start a problem like this? Write out what we're given, and the biggest part of that I think I saw a few people struggling with is, what is potassium sulfate? So who wants to volunteer the formula for potassium sulfate? Jean-Paul? Potassium and sulfate. We good? What did we need to tweak?
There needs to be 2 potassium.
Every potassium has a 1 plus charge. Every sulfate has a 2 minus, so we have to have 2 potassiums in every one. What I want us to keep in mind is that when that dissolves in water, if it dissolves, first of all, does it dissolve? Okay, so we look at our solubility chart, potassium sulfate soluble. It's a good step to throw in there. What does it generate when it dissolves? Maybe everyone write down really quick on your paper. When that dissolves in water, what is there afterwards? And how many of each? Okay, can I get a volunteer? Hand raised. What do we get when potassium sulfate dissolves in water? Lena? Okay, I'm going to have you tweak your wording, be a little more specific. Because what you said is 2 potassiums and 1 sulfate.
2 mole potassium, 2 potassium ions.
Ions. That's what I was looking for.
Sorry, that's not really.
Okay, so for every 1 potassium sulfate that dissolves, I saw a lot of people when they're working on a problem like this, they would instead say K2 plus. This implies that you have a bond between the 2 potassiums in a potassium sulfate, and that's not the case at all. This is 2 of the potassium ions is what's shown in that formula up there. When it goes into water, it breaks apart. So how many total particles or ions do we get for every 1 potassium sulfate that dissolves? What's the total number of ions for every 1 potassium sulfate that we get? It's not a trick question. How many? So on the left side of this equation, we have 0 ions that are separated until we describe it dissolving in water, and then how many individual ions are there?
Oh.
There's 2 here, there's 1 here, so we have 3 ions. If we started with 1 mole of potassium sulfate, how many moles of ions do we form? Three moles of potassium, 1 mole of potassium sulfate gives how many moles of ions? 3 moles. So if we have 1 mole K2, SO4, when it dissolves in water, we get 3 moles of ions. Am I doing anything tricky yet? That's a conversion factor.
What just happened? Was that the answer?
No.
Oh,
So if you knew how many moles of potassium sulfate you have, could you figure out how many moles of ions you have? With this new conversion factor that you probably could figure out on your own, but we walked through together. Okay, so go ahead and use what we just did to figure out how many moles of ions are in the solution. I'm going to give you 1 more minute. The screen's frozen, so I'll keep an eye on my watch. 1 more minute, and then we'll walk through this.
Where do you get that there's 3 moles of ions? 2 potassium. Right, that makes sense.
That helpful. That did it.
And because
That did it.
That broke the barrier.
Yes.
it's going to be like an osmole. So I'm not going to say how many molecules there are. We're going to go straight from moles. And then for every 1 mole of this,
Oh, okay. So, yeah.
that makes use that bottom equation.
So we need the 1 mole of K equals to 1
Maybe.
mole of
Didn't answer your question necessarily, but this is where we get the conversion factor from. So the main thing we should focus on, right? Doesn't matter if it's
I haven't even, I'm still writing it down.
3 ions or 1 dozen, 3 dozen. That whole just means that as long as you do the same thing over. So for every 1 of those, whatever the unit is, times that number of ions. So it's because we have 2 starting with compound water, then we have the separate. Okay, now it's Okay, so let's go ahead and talk through
That's so not right.
You don't think that's right?
how we would actually answer this question. Would anyone like to volunteer to walk us through it? Sebastian, is that you volunteering? Discussion. Okay, great. So I think you meant 1 mole of potassium sulfate on the top, is that right? Okay. Over. What's the molar mass of potassium sulfate? 174 point. And once again, if you're comfortable with calculating the molar mass in class, we're going to Google that. So hopefully you Googled it. Or even if you do calculate it, Google it to check it. Okay? And then what did you do next? So what would your next conversion factor be? Did you do that, or you didn't do another conversion factor? So if we look through each one of these steps here, we said, well, how heavy is the potassium sulfate? That doesn't help us figure out how many of them there are. So we use a molar mass to figure out how many moles there are. And then if we know how many moles, we can figure out how many ions because we have a 1-to-3 ratio. So our final answer is in unit of moles of ions. What numeric value did we get? I heard 1.35. Is that close?
No.
Is that the right number of sig figs?
Seems right. 3 sig.
We start with 3 sig figs. We don't use molar mass or an exact ratio to change that. So sounds reasonable. Is there another way we could answer this question?
Oh no. Always there.
So what we said is, if we know the number of moles of potassium sulfate, what's the ratio of how many total ions in every mole? We could have said, in this ratio here, what if I had wanted to know how many potassium ions there are instead? What would this ratio be? If I just wanted to know the number of moles of potassium ions, 2 moles of potassium ions for 1 mole of potassium sulfate. What about sulfate? 1 mole of sulfate ions to 1 mole of potassium sulfate. So some people might have chosen to do that. So here's the way that we did it. We could have found the moles of potassium ions, the moles of sulfate ions, and how are these 2 moles going to relate to this top number? The total number of moles is how many potassium ions plus how many sulfate ions. We add those together and we should get this value. Both of those ways are fine. Questions? So this is it is in line with the net ionic equations that we're doing, because we have to think about if we have a salt that's aqueous, if it dissolves in water, what does it break up into and how many does it break up into? So we're going to spend a little bit more time with that later on today. So let's add to that, and let's ask the next question. I think that this is on your worksheet. My timer's busted today, huh? Oh, it works there. Okay. So now we're going to take 1 mole of each one of these compounds here, and we're going to put them in water. Which solution is going to have the highest number of dissolved ions? Go ahead and think through it on your own first, and then maybe talk to your neighbor. And then click in your answer.
Yeah, because this is the NH4 is the it's the only one that's two carbons, two hydrogens.
This essentially is that. If I had my nursing backpack, I would.
I mean, it's still I think I both must have it's to cut down the length of the barrel, but technically not. Twisted
I thought I'd see some salt.
That's why I chose this place. I will see my watching this vending machine. You can go to the
Go out of my way. Okay, it looks like we have a really clear answer. Majority of people picked C. All right, so let's talk through why that is. So how do we approach this? How do we get to the conclusion that C is the right answer? Can someone talk us through that, please? Chris, do you want to talk through it?
I just put like 3 magnesium 2 plus 2 phosphate 2 minus, and then I looked at the numbers and I was like, oh, that's 5, and then that's bigger than the other ones, which are if you want me to list these out, I can.
So let's go through. So each one of these, we see we have 3 ammoniums for every 1 phosphate. So if that dissolves, we have 4 total ions. How many do we get with magnesium chloride? 3 ions. What about ammonium chloride?
2.
And what about the last one? What do you think about the last one? How many ions do we get if we dissolve that?
3. Oh, 0?
Why? Why is that a 0? What are your ions in that compound? Where's your metal? Where's your non-metal?
Not false.
That is a molecular compound. There are no ionic bonds in that molecule. So we're not going to think that those things separate when they go in water. So then with that said, we have a clear winner. So why is that answer wrong? So Shelby, you want to describe? It's not soluble.
That's right.
So this question had 2 parts.
We debated that between us.
Okay, so this question had 2 parts. So one is how many ions would each make if it dissolved? If you start with a mole of ammonium phosphate, you're going to get 4 moles of ions. If it dissolves. If it doesn't dissolve, you're not going to get any ions. So if we look at our chart, we find that magnesium phosphate is not soluble. So if magnesium phosphate is not soluble, we're not going to have any ions. So hopefully you were able to get the simulation to work in your homework, the JavaScript. Okay, if you didn't, come see me after class. I'll try to help you get started on that. But that kind of shows, it visualizes what happens to these compounds if they're dissolved or not dissolved. So it's actually a really good simulation. That's why I tried to get you to do it, because you actually see what's happening on a molecular atomic level. Okay, so our answer is the one that dissolves that has the most number of ions. One thing that is really important to keep in mind here is that your polyatomic ions, these do not dissolve into nitrogen and 4 hydrogens. That polyatomic ion stays together. That's why I needed to train you earlier on this semester to recognize polyatomic ions as a cohesive chunk of atoms that are molecularly bound. So before I go on any further, let's do this office hours thing. I looked at my schedule and I realized that I will not be here Wednesday night for the exam. I knew that. I'm going to be on a plane. But unlike my last trip, I'm actually leaving a little bit earlier in the day, and so I can't hold my regular office hours right before the exam. I would really, really, really love to see a lot of you in office hours. Office hours are a really good time where we set up problems like this. We work through them. People bring in homework problems. We struggle with them, and I try to be there to support you. So we do it as a group kind of activity, and I want to know which of these times might be available for that you might consider coming. So I'm going to go through the times listed on tomorrow and Wednesday and see which ones of those we think we'd have a lot of people, and I can open those up as office hours. And it's not 1 hour blocks. I can do multiple. I just kind of wanted to split it up earlier. Sarah, do you want to add something?
I was going to ask to see if I could hold your regular office hours.
That's a great idea. So Sarah has offered to also do, you have availability 3:30 to 5?
That's what I'm talking about.
Okay, so
Right there.
Sarah is going to save the day for Wednesday's regular office hours before the exam, so you're welcome to come and work with her. In addition to this, maybe can I just have a show of hands if you think you would like to come to the hours? I'm going to go one at a time. Raise your hand, and I'll try to get a rough idea which ones are the most popular, and I'll add those. Or if there's many that are popular, we'll do those. Okay? So Tuesday, tomorrow, 12 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5. Okay, so it looks like, let's do 3:30 to 5 tomorrow, and let's do 12 to 1:30 or 12:30 to 2. Which would be better?
12 to 2.
The whole time?
12 to 5.
I'll just be sitting here, just come hang out. I make lattes, so come have a latte. Okay, but I really want you guys to come. My job is to help you succeed in this class. And one of the best ways I can do that, as well as class, is to have you come to my office hours. So please bring your food, hang out. We'll do chemistry from 12 to 2. I'll have an hour-and-a-half break, and then we'll start again at 3:30. Okay? Looks like that captured 2 different populations of students. So then on Wednesday, if you're going to one of these 2, then you don't necessarily need to throw your hat in here. But if you also would want to come from 9 to 10 on Wednesday, raise your hands. This is in addition to the 3 that you've already seen. 9 to 10, 10 to 11, 11 to 12. Okay, so let's do 10 to 11:30. Would that work?
Yes. What about that? Who's doing the 3:30? You know where she's doing that?
Okay, so we've got a lot of time dedicated to help you get comfortable in the next 2 days. Yes? So, Sarah, where do you want to hold these? I don't know. I'm not going to be there to let you in, so I'm not sure if that's what I was talking about. How about let's do Science Lab 263? It's a little cold.
A little.
SLB 263. Okay, the rest of these are going to be in ETAS 125, which is my regular office hour space. Any questions on what we're offering or when? If you have not yet been to office hours, try it.
They're great.
See if it's helpful. We have a couple of people who have been regularly who approve this message. Okay. Great. And this can be bring your own question, or you can kind of tag along with what people are working on. You don't have to have a question to show up to these. All right. Any questions? You can bring your sister. Absolutely. Okay. So, our learning objectives for today. Predict the number of moles of ions in solution for any compound. Can you do this?
Yes.
Can you do it better anyway now?
Yes.
Okay. If you can't, perfect. Come tomorrow at office hours. We'll work through this. All right. And then I want you to determine the type of reaction if you see a reaction written out. And so that's going to be precipitation, acid-base, redox, and we're going to work on that for the rest of class. And I guess the last one down at the bottom, write the net ionic equation confidently, which is building off of what we just worked on for the number of ions. You have to be able to predict what something dissolves into. Okay, so on your sheet of paper, you have these 3 different types of reactions. You got a little explanation from me last night in an emailed announcement yesterday afternoon. Hopefully you saw that. There should be... Is that an extra, Savasia? Yep. Great. I printed out 60 of them, so there should be some floating around. It looks like there's another stack back behind the key there. So what I want you to do is I want you to write down, brainstorm with your neighbor, what classifies something as a precipitation, what's an acid-base, what's a redox. Go ahead and write down what you know, and then we'll make a better list together, and then we'll practice identifying them and add to that list.
I know acid-base and redox.
Googling that.
Google won't help very well. Maybe even more today.
It's super technical, so do what you know for now.
Well, I was just going to write there technology. Yeah. Is it that? Very
think I saw a video when I subscribed and I was like, I don't need to do that. And then I never watched
This doesn't have to be definitions, this can be what comes to mind, what do you know, we're going to build on this list, so put some ideas down, what's precipitation, what's different from that space, what's different from that.
Let's see what they are.
one compound is oxidized and the other is reduced.
When they is
Very good question. I'll leave that for another day.
like today.
But I got it right there.
All it is
Transfer, and they both.
it's all about
Displacement combustion, it's all.
which is all transferable.
So they're all oxidation reductions except for double displacement, which is not an oxidation.
Because it's not.
Because it does not involve a change in oxidation state. That's what my notes say.
That's from last one. From very technical. It's very technical.
The loss of an electron reduction is a gain of an electron transfer of an electron.
Redux. Oxidation. Reduction.
And I just think that it's all of them except for double displacement.
Oil. Huh? Oil.
Oxidation is loss, reduction equals gain. Yeah, it worked. Oxidation is loss, reduction is gain.
I need
Someone has had caffeine today.
Lots.
I haven't had mine yet.
I'm drinking my coffee.
Okay, I would like some brave souls who haven't talked in class in a little while, a few days at least, to volunteer some things they wrote down. We're going to start with precipitation. I'd love for you to toss your ideas in. This is just a brainstorming session. Don't feel like your answer is right or wrong. Kaya, thank you for starting us off.
Precipitation reaction, it starts with two aqueous solutions, and when they combine and form, they put out a solid in another aqueous.
Maybe this is over-abbreviated. So you start with aqueous reactants, and then chemical reaction happens, and there's a solid and something aqueous left over. Okay? Who wants to add to that? It can be some based on something you saw, based on something you've done. Have you seen these types of reactions before?
Yep. Never.
What do they look like when they happen? So that solid, when it forms, it's not just like a big chunk that falls to the bottom, right? It gets cloudy first, and then what happens?
Oh, yeah, put it in the spinner.
And then what do you get at the bottom? You get some sort of pellet or precipitate. Precipitate. Is that close?
Yep.
Precipitate. Okay. And the one that I always think of is precipitation. When we see that in the normal weather, it just means you have rain, so something is falling down. So gravity pulls something from one phase out. And so precipitation is the solid chunks settling out. Okay? I like it. Can I get a new voice giving some idea of an acid-base reaction? What comes to mind when we think of acid-base? Okay, so Dylan is quietly saying neutralization is something that comes to mind. Great. What else can we add to that? Justin? Okay, so they can involve OH, but I'm going to dig in a little bit deeper. What type of OH, or what are we missing about that OH? What's that? Okay, so we're going to get there in 1 second. If we're going to talk about OH, though, if you drew the Lewis structure, you won't be able to do it without the negative charge. So OH minuses can be involved. Okay, but they're not required. So Taylor, what were you saying?
I said the H plus ion transfers from one reactant to the other.
So this is the simplest form of a definition for an acid-base reaction. Is that you have an H on one atom, on one molecule, that's transferred as without its electron to the other. So whenever we see a transfer of an H from one side to the other, doesn't bring us electron, then that's an acid-base reaction. All right, what about our redox? Can I get a new voice for what we think of when we think of redox? Can I get Maddie or Caitlin? What did you guys write down? Okay. So I'm going to extract that very last line was the most important thing. It was great. So the most important part of what you said is that the charge changes. So if the charge changes from reactant to product, then what is transferring in a redox reaction? So you start with a metal that's a solid sometimes, and you end up with metal which is aqueous, which means that it has a charge. That is one of the possible ways we can have a redox reaction. So a redox happens because we start with the same number of electrons and protons, and then we end up with it's the same metal, so the number of protons doesn't change, but the number of electrons would. There are many other ways that we can have electrons transfer. It doesn't have to be with a metal, but the example that Caitlin was using was a metal, which is a very common way we look at redox reactions. And I think that I have a more official version of this. I think this is animated. Do you mind if I do that? Or do you need to write down what's there? Can I go? Okay. Same basic exact thing that we just said. Start with things that are dissolved. You end up with a solid for precipitation. Acid-base, we're transferring a H plus ion. And in chemistry, we refer to that as a proton. Does anyone know why we refer to an H plus ion as a proton? So if we go to the periodic table, hydrogen is defined as one proton. But if we have hydrogen like that, how many electrons does it have? There's no charge. So if the charge is 0, we have one proton and one electron. What about H plus, though? How many electrons does that have? 0 electrons. So that's just one proton. And so in chemistry language, we just kind of refer to something that's literally one proton, it's H plus ions. We just say it's a transfer of a proton. Okay? And then the last one, if we're transferring electrons, exactly like Caitlin was saying, we start with a metal that might be a solid, and afterwards it has 2 less electrons than it did to start with. Or we can look at the redox reaction, because copper has 2 more protons and electrons here, the +2 charge, and the product, it gained 2 electrons. So the purpose of what I want you to be able to do for Wednesday is just look at a reaction and say it's a precipitation, an acid base, or a redox. We're going to spend more time with what these actually are and what terms we have, so what's being reduced, what's being oxidized, and same thing up here. We're going to do that after exam 3. So let's practice that a little bit. Let's look at these reactions that we have. And I think I have these set out. Question number 4. Before you click in this exact one, try to go through all 4 of these and decide if you can figure out, is each one precipitation, acid base, or redox? Go through all 4 reactions and try to label it. And if you get stuck, work with the person next to you. So go ahead and on your sheet, so when we're walking around we can see, go ahead and write next to each one what you think it might be. If you use pencil, you can always erase it. Or if you use pen, you can cross it out.
Barometric minus thick pressure. I'll give you the pressure of your eye height. This is what you measure from the barometer. This comes from the table. Actually, this is 764 is the volume pressure estimate. They only use that one for this job.
Oh, it's acid base. Because it looks like it's neutralizing something, right? Because there's also the OH
With this one.
It looks like it's neutralizing to
Okay. What's the charge here? What's the charge here? What's the charge for C?
Let's say 2.
Okay.
Give you a little grace.
So, in this instance, what's the charge?
Oh no,
Solid doesn't have charge, so what is it? So, we'll have to go from positive to beginning or possibility? Yeah, I take mine off. I'm ready. So it is. If there's a transfer of electrons, you have. Still, don't go too far. As long as you see a transfer of electrons, that is considered a. It's all just precipitation, but it's redox mostly. Because you really can't tell the difference between solid zinc and solid copper. So the majority of it is redox. It's both.
Okay, we have 38 responses. Go ahead and click in your response to the first one. Okay, I think we have a couple more. I think we're at 46, is that right? All right, we're going to go ahead and close out. So if we look at this reaction, can I have someone talk through how we look at the reaction that's written up here and make a decision for what type of reaction it is? Maybe talk through the process. Jay, you want to talk through the process you used to make a decision? Nice and loud, please. Great.
And then if it were an acid, then it would have to either be neutral or hydrogen would have to transfer to the reactant.
Okay, so we'd have to have the transfer of an H plus ion.
Yeah.
Okay? And so nothing stood out to you immediately. What about redox?
It had to be like a solid.
Sometimes we have to have a transfer of electrons. So the most likely place in this class, at least for this exam, is you'll look at the metal. If the metal had one charge on one side and a different charge on the other, it meant it had to gain or lose electrons. So we only have one metal here, sodium. What's the charge on the left side? Positive 1. On the right side?
Oh, that's right. All the way to the right.
Plus 1, plus 1. So for now in this class, we're going to say that we didn't have a metal that changed charge. So it's not a redox. So does anyone else want to maybe add to the discussion that we had? Carmen?
That's it, my company way. I personally picked acid
You said it was an acid-base reaction. Why?
because it had the states. I chose it by the states. I don't know if that was right.
Okay, what about the states?
Like you have 2 aqueous, 1 liquid, well 3 aqueous and 1 liquid.
Okay.
And so from the example we had on the previous slide that I wrote down, and when I used to study, I compared it with acid.
Okay. So one of the very common features that you saw was that you produce water as a liquid. So that can be something that you use. Taylor, did you want to add?
I was going to say good. I said acid because it just seemed like it's a lot of hydrogen, and it just seemed like they moved to the other side and became like different items.
Okay, so there's 2 parts. One I love, and one is a common pet peeve or a common misconception. So the common misconception is that if there's hydrogens, then it can be an acid-base reaction. And that's not true. But the second part you said was great. You said that where they are changed. That's what we're looking for. We're looking for is the hydrogen in a different place from where it started and where we ended the reaction. So can anyone pick out which hydrogen that might have been? So in lab, you've used double displacement where you're switching partners. But here, what I want you to keep in mind is that these hydrogens didn't change from left to right. But that one did. It's no longer there afterwards. It was replaced by a sodium. And what that means is that if it could go with the sodium instead of the H, and it's still neutral, that means that hydrogen must have left as an H+. Because here, it has an H+, and it's neutral. Here, It doesn't have the H plus, but it has an Na plus, and it's still neutral. The other way to look at it is this is acetate. You guys recognize the polyatomic ion acetate? We know it's -1, so that can be a plus. And so that combines. So in essence, going back to what Jocelyn said earlier, an OH minus was involved in this case because if we dissolve this, we have an OH minus and an Na plus, and it combined with an H plus. And when it did, that forms water. So that is one of the common things that you see with an acid-base reaction is you form water and a salt. But that's not always the case. So don't get lured into thinking about that as the only time that happens. Another example, let me see if I have it here. Yeah, let's do this. Okay, this is kind of a jacked up equation, but it drives the point home. Can you see how this is an acid-base reaction as well?
Let's take a look at it. Because it's so involved. Wait a minute.
Kind of jacked up. This is not the best example. It's just what came to my head as I'm standing in front of a class of 50 people.
Wait, can you show it why?
We had a hydrogen attached to the nitrogen. Afterwards, it's gone. There were 4 before, there's 3 after. The water gained 1 hydrogen.
So you're thinking that's what?
This is hydronium. It's a polyatomic ion, H3O plus. So what you want to look at is, from the left side to the right side, does any molecule gain or lose H pluses? And that's an example, another terrible example. And we're going to get rid of that before anyone takes a picture of it, because it's really bad. But what I'm saying is you don't have to have liquid water as a product for it to be an acid base. Just look, is there a hydrogen ion transfer? Okay, let's go to the next one. Oh, wait, last thing. Next thing I wanted to do was... No, we're good. So let's go ahead and categorize this one. We have 37 responses, a couple more. Can I get a volunteer to talk through the process of this one? Can I get someone in this middle section right here to volunteer? Great. Morgan, thank you.
I'm not great, but I picked A precipitation because there's 2 aqueous and it forms solid.
And an aqueous. And the big take-home of a precipitation reaction is, over on the left side, before this reaction happened, we had 4 ions. We had 4 different types of ions. Sorry, not 4 of them. We had 4 different types of ions. And when they're allowed to move around in solution, they bump into each other. When the magnesium bumps back into the chloride, nothing happens. But when the magnesium bumps into the phosphate, then they're going to form a solid, and they're going to form precipitate.
So anytime we see like the aqueous, solid aqueous, can be precipitation?
No. So the reason why you can't just say that anytime you see aqueous, solid aqueous, that it's precipitation, is sometimes that might be a redox reaction too. So you need to look at a metal, because that solid might have been magnesium solid, in which case it's not a precipitate, it changed states. And I don't know if I have examples of that right now, but you need to look. So what's the terminology we use for this type of reaction in lab, besides precipitation?
Cloudy.
It is visually cloudy, yes, I agree. But it has to be a double displacement reaction. that forms the solid. Maybe that's a little more clear definition-wise, Taylor? Okay. Because if it's just something that goes from aqueous to solid, but it's by itself, then it's not a double displacement. It's about the fact that two ions are more strongly associated with each other, and they push all the water out, which makes them solid, and they sink to the bottom. All right, let's go ahead and do the next one. And by the way, we had 99% agreement on that last one. So seems like we're feeling okay on precipitation. All right, what about this one? Are we in agreement on this one? Go ahead and check with your neighbor. Click on your answer. All right, we got 47. Closing out. All right, who wants to explain the process for this one? Can I get someone in that back corner of the room? Back 2 or 3 rows. Would anyone like to volunteer? Thank you, Jessica.
Redox.
Why did you say it's a redox reaction?
Metal solid of zinc doesn't have a charge, so the charge carries over from the CuSO4 into the product.
Okay, so what is the charge of the zinc on the right side of the reaction? 2+, because every sulfate is 2-. Okay? And the copper on the right side is 0. Copper on the left side is 2+. Zinc on the left side is 0. So what we know here is that the zinc went from the same number of electrons and protons to having 2 more protons and electrons. So that zinc gave up 2 of its electrons to copper. So that's a transfer of electrons. That's what we mean by redox. So I agree. This is a very typical redox reaction. All right, let's go ahead and do the last one. A couple more seconds. And we're going to go ahead and close this out. Can I hear from Brendan on this one? What did you answer and how? Why did you say no reaction? Great, so then you went through every one, you looked at the charges. What's the charge of calcium on the left and the right? What's the charge of lead on the left and the right? And you found no change. So then that rules out precipitation, redox. So there's only a few hydrogens, and they're here in this acetate, but they're still there in the products. So, I agree. Well done. Okay. Any questions on that one? So, go ahead now and work through each one of these. 4 on the next page. Question number 5. I want you to figure out what type of reaction they are. You can go ahead and balance them as well, if they are not balanced. And the other thing, if you notice in question 6, after you identify the type of reaction, I want you to be thinking about spectator ions and net ionic equations. So we're going to take 5 minutes for you to work on these 4 reactions.
I know, look, there's already so many numbers on it.
Plus quickly is 2 plus.
Hold on, it's done, let's just go with it. Let's see if the precipitant is done.
Well,
I think
it's
the
a
first one that's like that.
but it's still the same.
Stationary is just so office supplies would include or incredibly lost and
We have one that's not.
everything that we can do. Lost.
On figuring out the type of
On Redux specifically.
Okay, so if you were to give that thing a charge, you charge it.
Sorry, it's balanced, anything.
There's no charge, I agree. What about the comforter?
Isn't it the same thing that was one day?
It's very similar. It's going opposite direction.
Oh, okay. And then this one I have a charge of 2. Well, it's neutral now.
Okay, so talk through the process.
It's Redux because the transfer of electrons from zinc to copper because like it's going from neutral to 2 plus, and then this is going to neutral because this is 2 plus. Because this was 2 minus previously, copper 2.
Copper 2 plus
Yeah,
with
copper
2
2 plus
sulfurs.
with 2 sulfurs.
Exactly. So you just need to look because the metal doesn't change. Second phase oxidation or full charge.
Where's the?
It doesn't. So here, this also.
I remember the homework did something about actually no, I don't think the homework did something, but like redirected to a page that talked about oxidation and like assigning a number to it.
Yeah, for now, that's why I said for now.
Don't worry about that.
It's just, think about the charge of any metal. So what about here? Does the charge of barium change from there? Does the charge of potassium change from there? That's what you need to look for. No, that's not. That what?
You're just looking at the chamber.
Okay, about 1.5 more minutes to try to identify the balance of the reaction.
Did you balance this anyway, this first one? Yeah, I don't think anything's.
Because this one's not balanced. It's not balanced because it's 2 K and 3.
So you don't have enough charges.
Because the barium is a 2 plus, and that's why there's a 2. And then that means that there must be 2 plus.
Let's go through each one of these 4 and talk about the process and how we decide what type of reaction they are. Can I get 4 volunteers? Ideally, who we haven't heard from yet today in class. But thank you, Shelby. 4 volunteers. Donald, 1. Who else? Summer, would you like to do one? Okay, so Summer's doing 1. Monica's doing 1. And who's our 4th volunteer? Okay, so we've got Donald, you're going to do the 4th one. All right, so Summer, you want to go ahead and talk through the first one you said? What type of reaction did you say and why? Okay, why did you say it's precipitation?
And it's balanced. And it's 2 aqueous made one-sided and
Okay, and it was a double displacement. So let's also add that additional qualification in there. Okay, so you said precipitation. Any qualms with that? That's a pretty good agreement. Okay, fantastic. I agree. Number 2. Who was doing number 2? Was that Monica? Or B on there?
Okay, it was already done. And so, okay, so I went for the charges. Apparently, the zinc is a 0 charge.
Okay, starts as a 0 charge and goes to?
Goes to a +2.
Great. So we know already, just that alone, we know it's a redox reaction. We don't even have to do the rest. But we can see where do those electrons go, because it loses electrons. So when we look at the copper, and what charge does copper have on the left versus the right?
It was a +2.
Yep. And it goes to? So we can follow that the charge changes from left to right side for each of the metals.
Can you say that redox is single displacement?
Nope.
Okay.
Not all redox are single displacement. I don't think. Okay, number 3.
I said I will.
Go ahead, Taylor.
Well, at first I had the galaxy, and I put a 2 on the left side in front of the K and a 3. And then I put another 2 on the right side in front of the KCL. And I said no risk. But I don't know if it's
Any disagreements with that? Okay, and here's the secret. No reaction means that we have 4 ions, barium, 2+, chloride, potassium, and nitrate. When all 4 of those ions are floating around freely in water, when they bump into each other, they're not attractive enough to push out the water, and they keep going as individual ions. So really, on the right side, we just write this out to check, is this soluble, is this soluble? If all 4 pairings are soluble, no reaction. Nothing happens. We just have a whole bunch of ions floating around. Okay, Donald, last one.
I said it was an acid base
Why?
because I balanced it first, and I put a 2 in front of the H2O, and a 2 in front of the hydrogen,
The reactant?
in front of the acid. Yeah, that's what the
So it's actually the lactate. It's actually, this is lactic acid. It's a little more complicated. Fair enough. Just has, it would be if it was just O2, a CO2H here, but it's got a lot more going on. So it's lactic acid, what builds up in your muscles after you run.
And then you have the hydrogen transfers from lactic acid, and it helps form H2O.
And if we're going to pick it out, this is the hydrogen that's there before. If you notice everything else. Did I mess that up? I did mess that up.
He did.
There's supposed to be CH3 there. That's a typo. Oops. Okay, so there's a transfer of a hydrogen. Okay.
So on number 3, we could have just looked and saw that all of the things are aqueous, and that was just automatically in the reaction.
By seeing that everything is aqueous all the way through, I would still want to check to make sure that no metal change charges. Because we can have redox reactions where we go from a +2 to a +3, and that's a redox reaction. Good question. Okay, so then if we look at that first reaction, Are there any spectator ions in this reaction?
Yes.
Go ahead and click in your response.
Which ones put A or B?
What the
Oh, never mind.
or it's called,
Just joking.
Nitrite.
Make sure you're paying attention.
and
8.
You can't put more than one answer.
Why can't you put more?
Yeah, we have it set to,
There's 10 answers.
So just.
That's why I used the wrong entry type. Okay, try again. Enter all the numbers that apply and hit send. So if you think it's 1 and 2, hit 12, send. Not bad.
two, A, B, you know, they're all the same. You need to have kind of like a star in the corner so you know you need to change.
Let's do another 10 seconds. We're doing this so we can kind of get a little pace going in recognizing this.
In about 3.
And hopefully after we do this the first time, you'll be a little more comfortable the second time. So I'm going to go ahead and close this out. And our majority answer is 23. 2 and 3.
Really? I did something wrong with it. That's not what I heard.
How do we come up with that answer? Chris?
I learned this one from Miss Jo.
Nice and loud.
Where if you look at the reaction and you find like on both sides that something has stayed aqueous, then it's a spectator.
Boom. Everyone hear that?
Yes.
So Chris said, if something stays aqueous on both sides, it is a spectator. That's the definition. It doesn't react. So aqueous before, aqueous after. If we look at this reaction, is calcium aqueous before and after? No. Nope. Is nitrate?
Yes.
Yes. Is manganese?
Yes.
Is sulfate? Okay, so we can go through and we can kind of do that. We can say, okay, and one of the tricks too is if it's a precipitation reaction, whatever your aqueous is afterwards is by definition your spectators because those didn't react. So you can see those before as well. Okay, so then if we wanted to write our net ionic equation, can we do that? So if you notice down below in question number 7, I have some blank space. What would I write for my net ionic equation for this? Based off of... Not the whole left side. So what part of the left side do we keep? What else do we keep on the left side?
SO4, 2 plus.
2 minus. And then on the right side? Is this a little bit simpler than writing out the total ionic and then the net ionics? Either way is fine. I don't really mind whichever way you go about it. Can we do that super quick for the next one? All right, I think we can do this super quick. Go ahead and say for the second one, for B on your page, which are the spectator ions and hit send. And then think about what the net ionic is. Couple more seconds. What is our spectator ion or ions in this reaction? And we're closing out. What do we say? Majority of people say 3. If we look at our redox reaction, this changes from left to right. Copper changes from left to right, but sulfate stays aqueous in both. So that's our only spectator on. What's that?
So that makes it so much easier to understand.
Okay. Could you do that for each of the later reactions too? So I want you to practice on those. Hold on. Before you go, I kind of want to pull up the last question because I think you might find it valuable. So the last question on here is this question. Remember in our class, we've been doing a lot of calculations about what's the limiting reactant. So go ahead and read this really quickly. Just from this information, can we determine what the limiting reactant is? It's not a trick question. Okay, a couple more seconds. Can I have someone explain why you picked the answer you did? I know I'm going over. I apologize. This is the last couple minutes I have with you before you take an exam. So, Jocelyn? Can you say it a little louder? Okay. Donald, you want to add to that? Okay.
Because we don't know anything else besides that we have two products with a certain amount of grams, like what's the ratio? It could be 3 to 1 to make something. So you could use the 863 before you use the 557.
But here's the beauty, is that in order to find both of these, you would need to know the stoichiometric ratio. So I agree with Jocelyn. That if we calculate with our stoichiometric ratio and our molar masses, molar ratio, all that, whichever one gives us the ability to make the least product is going to be our limiting reactant. All right. I wish you the best of luck on the exam. Please come and work through these types of problems over the next couple days. Practice the ones I gave you if you want to. What's up, Chris?